In this example, we are going to graph the set of parametric equations by making a table of values. The graph that we are going to create here is going to be known as a bicorn. Based on the hint, we're going to use increments of pi over 2, which is pretty helpful considering that if you look at the functions here, particularly y is going to be relatively busy. X here is going to just equal 4 sine of t, whereas y is equal to 4 cosine squared of t times the quantity 2 plus cosine of t, and that all is being divided by 3 plus sine squared of t. We do have restrictions on t as well, that t is between 0 and 2 pi, and that means if we're just doing increments of pi over 2, then that means we can stick to some pretty familiar values. So we can do 0, pi over 2, pi, 3 pi over 2, and 2 pi. That hopefully should be sufficient for us. If, though, you are so inclined to test other points, for example, if you wanted to test, let's say, 5 pi over 4, keep in mind that whatever x and y coordinate you get, that would show up in the sequence between pi and 3 pi over 2, because 5 pi over 4 is between those two values. So when you graph these points and connect them from one to the next, just keep in mind where that would be in the sequence if you do add additional points after your first set. But I can probably just stick to these. Now, even though y does look very complex because it has a lot going on, we should not need to use a calculator for this, because all the values that we plug in are increments of 0, pi over 2, etc., and we're just using sine and cosine, meaning that we're just going to have a lot of 1s, 0s, and negative 1s in this equation. Let's see what this would look like. First, I'll just take care of the x coordinates. I'll take care of all the x coordinates and then we'll deal with y. For the x coordinates, if I plug in 0 in for t here, well, sine of 0 is 0, so that's just going to give me 0 there. If I plug in pi halves in for t for the x equation, 4 sine of pi halves is 4 times 1, or just 4. If I plug in pi for sine of pi is 0. 3 pi halves in for sine of 3 pi halves is negative 1, so 4 times negative 1 is negative 4. And lastly, 2 pi, sine of 2 pi is 0 again, and that finishes off our x coordinates. Keep in mind that x is restricted to be between 0 and 2 pi, so there's nothing past this. We've got our beginning point and our ending point. Now we just need to take care of y. As I plug in my values and talk about them, I'll also show them here because this one's a little bit more complex. Well, let's say I plug in 0. I'm going to be plugging in 0 for every instance of t in this equation up here. If I plug in 0, cosine of 0 is 1. So that's going to be 1 squared. And that's going to be multiplied by 2 plus cosine of 0, which I have already said is 1. We will then divide that by 3 plus sine of 0 squared. Sine of 0 is 0, so that's 0 squared. So just 1s and 0s, really. If I evaluate all this, that will be 4 times 1 times 3. So that's 12 divided by 3, which gives me 4. If I plug in pi over 2, that's just going to change these 3 inputs, which I will now put in a different color for the next few equations, or next few examples. Cosine of pi over 2 is 0, so that'll give me 0 squared here. And then cosine of 0 again is, or cosine of pi over 2 again is 0. But in the denominator, I'll have sine squared of pi over 2, so that'll be 1 squared. However, I probably didn't even need to go that far, as on top, I'm going to be multiplying by 0. So that means this whole thing is just going to equal 0. Next with pi. If I plug in pi, cosine of pi is -1. So that'll be -1 squared. Then I plug in a -1 here as well for cosine. And then sine of pi is 0. So this is not going to equal 0. This will be 4 times 1, which is 4, times 2 minus 1 is 1. So that's just 4 divided by 3. So 4 divided by 3, or if you want to approximate that, 1.3 repeating. All right, then we continue. I can plug in 3 pi over 2. Cosine of 3 pi over 2 is 0, and we're also going to get 0 and -1 down here, but that's not really going to matter because the whole thing is still going to be multiplied by 0. So we're going to get another 0 output from that. And the last value I plug in is 2 pi. Cosine of 2 pi is 1, so that will be 1 squared there. Cosine of 2 pi I already said is 1. And then sine of 2 pi is 0, so it'll be 0 squared in the denominator. This is going to evaluate to equal the same thing as our first point because 4 times 1 times 3 is 12. We'll divide on the bottom here by 3. 12 divided by 3 is just 4. So we were able to get all these values here, and we didn't need to use a calculator, despite how complex y looked. Now, if you tested other values, like you tested 3 pi over 4 or 4 pi over 3 or something, then I would probably use a calculator to approximate y, as that is going to get relatively complex, even if we know sine and cosine of those values. But this hopefully should be enough. Our first point here is 0, 4. That puts us on the y-axis. That is our starting point. The second point we have is 4, 0. That puts us now on the x-axis. That is our second point. And then our third point here is 0, 4/3, or 1.3. So that'll put us about here again on the y-axis. That is our third point. Our fourth point is -4, 0, which puts us again on the x-axis in the negative direction this time. And then our fifth point is exactly the same as our first. So we are ending up exactly where we started. What this will look like, though, if you connect all these points, 1 is going to curve down towards 2, kind of like a circle. But then from there, it's going to abruptly shift and turn back towards 3. And on to our fourth point. And then back up to our top. Again, if you would like to test other points in between to verify some of these, by all means, you can do so. But this is what the bicorn will look like. The only thing we do need to include, though, is the orientation. Since we started up at the top and moved down towards this direction, based on our ordering of points, we should have orientation that follows like this. Down to the right, back to the left, and back to the top. That would be our graph of our bicorn.